Hello, good morning, everyone. Am I audible?
Yes, sir.
Okay. Is my voice clear to everyone? Hello. Shall we begin? Okay, let's begin. So where were we? We were proving the Hahn-Banach theorem. Let me state it again. So Hahn-Banach theorem says that suppose we have a vector space, say real vector space, and in X, so X is real vector space. In X, we have a sublinear map. The sublinear map is this P from X to R. We call it sublinear functional, which satisfies these two things. Then P of alpha X equal to alpha Px. And suppose we have suppose Z is a subspace of X and F is a linear functional on Z. So it's a linear functional. Which satisfies this inequality, and this is true for all X in Z. Then then Banach theorem says that there exists an extension of F, means there exists an F tilde which is linear functional from X to R, such that F tilde Z is F. Okay, and in fact, it will satisfy this inequality as well. Clear? Hello?
Yes, sir.
Please say something so that you you won't get bored or I won't get bored. Okay, please say something. Participate in conversation. Okay. So by proving this theorem, we were using John's lemma, and in fact, what we have shown so far is we have produced an F tilde. Okay, so proof. So far, what we have got is we produced an F tilde from its domain of definition to R, which satisfies F tilde X less than equal to Px for all X in dF tilde. Correct? Okay, so today what we do, we will prove that this dF tilde is nothing but X. Okay, so assume on contrary that this is not true. Assume on the contrary that dF tilde is not equal to X. This, but you know dF tilde is a subspace of X. So then there exists, this means there exists a y1 in x minus df tilde. Okay, so we have y1, we have df tilde. So you all know that df tilde, and this is a subspace, subspace of x. If you take this span of y1, this is again a subspace of x. Both these are subspaces of x. Okay. Now you do one thing. You take uh, a subspace y1 of x. Take y1, which will be a subspace of x spanned by df theta and y1. Okay. This is span of df theta comma y1. Okay, so you may say that y1 could be 0, but it's not true because y1 is in x, but y1 is not in df tilde, and you know 0 belongs to df tilde, so this means y1 is non-zero. So clearly y1 is non-zero. So this means any x in y1, any x in capital Y1 can be represented uniquely in this linear combination. So where this is y comes from df tilde plus alpha y1, where y belongs to df tilde. Okay, and so since y1 is the span of this df tilde and y1, so this representation is unique. So this representation is unique. Okay, so you in fact you may prove it. It's easy. So now we define another functional on y1. Define g1 on y1 are using f tilde by, so g1 is defined by y plus alpha y1, which is nothing but f tilde y plus alpha 6. Define g1 by this. Where the C is, we will choose the C, where C is real constant. So it's easy to see that G1 is linear. So it's an so for this you have to prove that G1, say x1, x2 is G1 x1 plus G2, sorry, G1 x2. So where is x1 comma x2, they belongs to y1. So this means x1 can be represented as some say z plus alpha y1. X2 is represented as y plus beta y1. Okay, so use this, and you can easily prove that g1 x1 plus x2 is g1 x1 plus g1 x2. And one more thing you have to prove, g1 alpha x is nothing but alpha of g1 x. Okay, so it is an exercise for you. So let's see the definition of g1 again. So G1 was defined as G1 plus G1 Y plus alpha Y1 is alpha Y plus alpha C. What happened when alpha is 0? Means, so what, so you know this Y1 contains, Y1 is span of df tilde comma Y1. So clearly df tilde is a subspace of Y1. Okay. So when we restrict this G1 to df tilde, what we get? So this means in this definition of G1, if we put alpha equal to 0, what you get is G1 Y equal to f tilde Y. And you know Y belongs to df tilde. So this means G1, when we restrict to df tilde, it is nothing but f tilde. Okay. So this clearly implies that G1 is uh, a proper extension of f tilde. And what does it mean by proper? Proper means this df tilde is a proper subset of I. Okay. So hmm. Now, if you remember that while when we start proving this theorem, we first define a set E, which was nothing but all extension of F. Okay. So this E is the set of linear functionals which are this is linear subspace. Okay, linear subspace of X, and in fact, Z is contained in Z dg, and G is an extension of F. And one more thing. Okay. So what will we do now? We will prove G1 belongs to this G1. See here, this G1. If we prove G1 belongs to E, so for showing G1 belongs to E, we have to show that Gx is less than equal to Px. Okay. So if we show that G1 belongs to E, then what contradiction we will get? We will get that f tilde is not a maximal element. Okay. So this means our assumption was wrong. What was our assumption? Our assumption was that df tilde, our assumption was here, df tilde is not equal to h. Okay. Okay, so let me write it. So what we will prove now, we will prove that G1 belongs to E. So now our claim is G1 is less than equal to Px. Okay, let's do that. So now our claim is G1 belongs to E. Okay, we will prove this. And how do we prove this? We will prove this by showing that given x is less than equal to px. Okay, so and yeah, so if we prove this, this means g1 belongs to E. This means f tilde is not a maximal element of E, which is a contradiction. So our assumption was wrong. This implies the f tilde equal to x. Then our job is done. So let's do the third case where we have to prove C1 belongs to E. This is our claim now. So for this, we have to choose C suitably such that G1 is less than equal to P. Sorry, P. So to show that, so we'll choose suitable C such that G1 satisfies given X less than equal to Px for all X P G1. Okay, so let's do this. So for this, we consider 2 points y and z in the f tilde. Okay, and use the definition of E. What is E? E is these are extension of f such that gx less than equal to px. Okay, so f tilde also belongs to E. So f tilde is an extension of f and f tilde less than equal to p. So from here f tilde say f tilde y minus z. See, f tilde is a linear functional. F tilde y minus z is nothing but f tilde y minus f tilde z, and you know f tilde y is okay. So this part f tilde y minus z is less than equal to p y minus z. Okay, so and you know p is a sublinear functional. So before we add, what we do, we add and subtract y1 and use definition of p, that is p is sublinear. We will get this. Okay, so this part is so far it's okay. So this implies if we take wait for 1 minute. So here, so let me write it in this as p of minus y1 minus z. Okay. Okay, if we bring this left hand side, so what we will get, this inequality. Okay, so and from here this part was p minus y1 minus z plus f tilde y minus f tilde z less than equal to p y plus y1. Okay, this implies this is nothing but p value minus z minus f tilde z less than equal to u. Now bring it here. So you get this inequality. Now, see, left hand side there is no y, in right hand side there is no z, correct? So you take supremum in left hand side and infimum over right hand side. So take supremum over z because yeah. So this side there is no y, this side there is no. So here no y, here no z. Okay, so we define m naught, set m naught as supremum over. So in left hand side y1 is fixed. So only thing that varies is z. Okay, take supremum over z df theta of left hand side, whatever left hand side, right there. Take m naught is this, and m1 is wait for 1 minute. Okay, yeah, everything is okay. Am I audible to everyone?
Yes, sir.
Hello? Okay. So you are not saying anything, so that's why I'm little worried. Okay, so we took supremum in left hand side, and now take so in this side y1 is fixed, and only thing that varies is y. Okay, so take y equal to, sorry, take m1 equal to infimum y varies df theta py plus y1. So since you know in left hand side there is no y, in right hand side there is no z, so this therefore m naught is less than equal to. So this comes from this inequality. Okay. So now for any element, any number between m naught and m1, or any c with m naught less than equal to c m1, what we have from by definition. So here m naught is less than equal to c, and what is m naught? M naught is supremum over all z of minus p minus y1 minus z minus f filter z. So m naught is less than equal to c. This implies minus p minus y1 minus z minus f filter z is less than equal to c, and this is true for all z in df filter because supremum, this m naught was less than equal to c. This means supremum was less than equal to c. So therefore it is true for all z df. Similarly, we have c less than equal to m1, and here what is m1? M1 is infimum of this. So the least thing is c is less than the least thing. Okay, whatever least quantity of this, c is less than that. This means c is even less than for all y in df filter Okay, so this is what we will get. Okay, two things. So let me put these two in rectangular box. Okay. Now we use the definition of G1. Let us recall it again. What was the definition of G1? What is G1? Did I define that? Okay, here we define. Let me write it again. See this G1 y plus alpha y1 is f tilde y plus alpha c. Let's write it again. So G1 y plus alpha y1 c. So this was G1. Okay. So I'm writing it here. So where this y belongs to the f tilde and you know alpha is any real number. Okay. So now we divide alpha in three parts: alpha positive, alpha 0, and alpha uh, alpha negative. Alpha negative, alpha equal to 0, and alpha positive. Okay. And what we have to show, our claim was G1 belong to E. So for this, what we have to show, G1 is an extension of F, and G1 is less than equal to P. Okay. So we have seen that G1 is an extension of F. What we have now proved is G1 less than equal to P. Okay, so we will prove that. So first case, when alpha is negative, so alpha is non-zero. Okay, put z equal to y by alpha here, not here, here. Okay. So what we will get? We will get minus p minus y1, z is minus y by alpha minus f tilde y by alpha less than equal to c. Okay, this implies minus p. This is alpha. What we will get 1 minute. This is minus y1 minus y by alpha minus f tilde. So this is 1 by alpha y less than equal to c. Okay. So this implies this is minus alpha p y1 minus y by alpha minus f tilde y less than equal to alpha c. Oh, but there is a problem. There is a problem. What is that problem? When we so this alpha is negative. This alpha is negative. So this inequality will get changed. 1 minute. So what we do, we don't write like this. What we do, we just multiply by minus alpha. Multiply by minus alpha. Now minus, since alpha is less than 0, minus alpha is greater than 0. So multiply this inequality by minus alpha, you will get minus y by alpha. Now this is minus alpha upon alpha, this is 1 less than equal to minus alpha c. Okay, and 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 use the definition of G1 here. So this, you know, y plus alpha y1 is an element of capital Y1, the subspace capital Y1. So you know, whenever x belongs to Y1, it can be represented as y plus alpha Y1. So write x equal to y plus alpha Y1. So what you obtain is G1 y plus alpha Y1 is tilde y plus alpha c, and from here f tilde y plus alpha c. See, f tilde y, you take this side, bring this part that side, you will get minus alpha p minus y1 minus y alpha. Okay, so there, now use p is sublinear. So this is minus alpha p minus y1 and minus py by alpha. So multiply it by minus alpha, so you will get y1 plus py. So this is nothing but here there is a problem. Let's not do this first. No, I have not written it correctly. This should be less than equal to. I do correct. No, I'm not doing it correctly. Let's do it in another way. So first use this second definition. So second definition says P of alpha x equal to alpha of px. Okay, use that here. So this is alpha into P of something. So it will be P of minus alpha minus y1 minus y by alpha. Correct? Okay. So this thing is P of alpha y1 minus y. Not minus, plus y. And this is nothing but, say, x1. So this is g1x. This is px. So from here, what we have seen, g1x is less than equal to px. So this part is done. When alpha is less than 0, we g1 belongs to p. When alpha equal to 0, there is nothing to prove. So it's easy. Case 2, when alpha is 0. When alpha is 0, say x, what was your x? X was y plus alpha y1. When alpha is 0, this is x equal to y. And you know, here you have G1 restricted 3 alpha dash is nothing but alpha dash. And by definition of E, f tilde dash, f tilde of x is less than equal to px. This is from the definition of. So there is nothing. Case third, when alpha is positive, again use the same trick. Put so this, now what we will do, we will put it here. So put y equal to y by alpha. So let's see. Okay, here it will be C less than equal to P y by alpha plus y1 minus f tilde y by alpha. So this is C less than equal to P y by alpha plus y1 minus f tilde alpha.
सब y को y
So,
by alpha कैसे लिख दिए? y is equal to y by alpha. Y is equal to y by alpha.
Okay, I'm putting, so this y is variable. Y is anything in df tilde, okay? Hello?
Yes, sir.
Y belong to df. So I'm putting y equal to y by, so when I do this, this means I am varying. So what I'm doing, say this was my df tilde, so this is df tilde, this part is df tilde, say this is my y. Now I am using any point in this subspace. Okay, I am replacing this y by any other point in this subspace. So for that, what I have to do, I just, so this y 1 by alpha is, what will be 1 by alpha? 1 by alpha is any scalar. Okay. Hello?
Yes, sir. Yes.
हाँ, so अगर मेरा पहले y यहाँ पर है, अब मैं उस y को मान लो मैं 2y लेना चाहता हूँ, तो एक मुझे y अपॉन 1/2 ऐसे कुछ लेना पड़ेगा. ठीक है, तो अभी मैं क्या कर रहा हूँ यहाँ पर, ये केवल देख रहा हूँ कि दूसरे पॉइंट के लिए क्या है. मैं y को रिप्लेस कर रहा हूँ किसी दूसरे पॉइंट से जो इस सब स्पेस में, ये दो सब स्पेस है. ठीक है,
ठीक है सर.
क्योंकि ये किसी भी डीएफ टिल्टा के लिए ट्रू था और आपको मालूम है डीएफ टिल्टा एक सब स्पेस है. डीएफ टिल्टा सब स्पेस है, मैं उसमें किसी भी स्केलर से मल्टीप्लाई करूंगा तो फिर से उसी का एलिमेंट आएगा. करेक्ट? हेलो?
Yes, sir.
If y belong to df tilde, if I multiply by any beta in y, so it will again be in df tilde.
Yes,
Correct?
sir.
So therefore, if this inequality is true, if this inequality is true for any y in df tilde, it will true for beta y as well. Correct? Correct or not? So, hello?
Yes, sir.
सही है ये?
हाँ, क्योंकि वो सब स्पेस है तो फिर.
हाँ, तो उसको, क्योंकि y तो आर्बिट्ररी पॉइंट था, उसको अभी एक पर्टिकुलर पॉइंट अल्फा और सी के बीच में रिलेशन देखो, तो मैं एक पर्टिकुलर ले लूं. ठीक है?
ठीक है सर.
ओके, so same trick here, multiply by alpha. So what you will get, alpha c less than equal to alpha p y by alpha plus y1 minus f tilde y by alpha alpha. Okay, so do this. This is p alpha y by alpha plus alpha y1 minus f tilde y by alpha. This will get cancelled, this will get cancelled. So this is p y plus alpha y1. You know p plus y plus alpha y1 is, this is x. So this is nothing but px minus f tilde y. Now use the definition of G1. What is G1x? G1x is, what is G1x? G1x is f tilde y plus alpha c. Okay. So from here, what you get? You get, see, this is alpha c, this is less than equal to px, less than equal to p, so alpha c less than equal to px minus f tilde y. This means when you bring this f tilde y this side, so it will be f tilde y plus alpha c. And it is less than equal to what? Px. Correct? So this implies G1x is less than equal to Px. So in each three cases, we saw that G1 is less than equal to P. So this implies G1 belongs to E. So we are done. We are done. This is what we wanted to prove, because after this point, what we will get that f tilde is not a maximal element, not a maximal element. Okay. So our assumption was wrong. Therefore, df tilde equal to x. So what we get? So we get an extension of f. This means f tilde is a linear functional from x to r, and such that whenever f tilde restricted to z, we have f. And one more thing, f tilde x is less than, and the theorem is proved. So when we started proving this theorem, I told you that we are doing this because we wanted to we wanted to see an existence of a linear functional. So even I gave you an example where there exists a linear functional in a subspace of dimension 1. So if you remember correctly, so what we did, we have a linear space and we have a non-zero point in X. What we did, we took a subspace Y, which is the span of Y naught, and I gave you an example of a linear functional from Y to R. Say, okay, Y to R says that f of, see, this Y is a subspace spanned by Y naught. So any element of Y, capital Y, is written in this form. Correct? So if we define f of alpha Y naught is alpha, then in this way we get a linear function. And I said that if we have a linear functional in one-dimensional subspace, and Banach theorem will guarantee that there exists a linear functional in whole of X. But in Banach theorem, you saw a sublinear functional. Without that, we did not prove this. For proving, we use something sublinear functional P from X to R. Okay. So can you give me an example of a sublinear functional on whole of X? So say we have a linear functional, linear space or a vector space, both are same. Say we have a linear space X. Can you give me an example of a sublinear functional in X? Any idea? Hello? Soumya? Hello?
Yes, sir.
हाँ बताइए.
सर आपकी वॉइस नहीं क्लियर आ रही है।
बिल्कुल
Please
नहीं है
repeat
क्या?
it again.
So let me write it. Okay, so this is a question. Suppose X is a vector space. Yeah. And give an example of a sublinear functional on X. This means give me an example from okay, give me an example of a map G from X to R such that G of X1 plus X2 is less than equal to G of X1 plus G of X2. Can you give me such example? So here X is a real, say, real vector space. Real vector space.
सर अभी तो नहीं आ रहा है।
अभी नहीं आ रहा। ओके, सो देखते हैं कोई एक एग्जांपल।
यस सर।
So you all know that we have a vector space X and X has a basis. Every vector space has a basis. You all know this. Do you agree with this statement? Hello?
Yes sir.
Okay. X is the X vector space and X has a basis. Say even. Suppose X is a finite dimensional vector space. So X can be X as a basis. So each element of X can be written in this form. Okay, where alpha I belong to R. You know this. And this representation is unique. Correct?
Yes sir.
If you remember L1 norm. So what was L1 norm? So now define a map G from X to R such that G of X is G of alpha 1 even alpha n en is given by alpha 1 to alpha n. Okay, and you may use this thing. So this clearly a linear functional, not a linear functional, but sublinear functional. Do you all agree that this is a norm? Hello? Is this a norm?
Yes sir.
Okay, so you have already seen that this is true for every norm. So since G is a linear, G is a norm, therefore G of X1 plus X2 is less than equal to. Okay. So this gives an example of sublinear function on X. Okay, you may see here you took a finite dimensional vector space You may take any vector space because every vector space has a basis and it can be written as a linear. So any element of X can be written as a linear combination of its basis. Correct?
Yes.
Yes.
Sir.
Yes, sir.
So this means now you have at least one sublinear functional, and using Hahn-Banach theorem, you may come up with many linear functionals on X. Okay, so here is a little exercise for you. So what is that exercise? Exercise says if P is sublinear, so P from X to R, this is sublinear, then we define a set M. This is sublevel sets. And gamma greater than 0, this is fixed. It's convex. So how do you prove such question? In such problem, how do you tackle such problem? You have to show that M is convex. So what is the definition of convex set? What is the definition of a convex set? Hello?
Yes, sir.
So what do we want to prove here? We want to prove M is convex. So how will we prove?
Alpha
idea?
x plus 1 minus alpha y c का element.
Okay. Okay. So x comma y in M. So you have to prove that alpha x plus 1 minus alpha y belong to M, where alpha belongs to 0 comma 1.
Alpha is from 0 to 1.
Correct. So for this, consider this, and P is sublinear. You will get this. You know Px is less than equal to gamma by definition of M.
Alpha.
So P of alpha x plus 1 minus alpha y less than equal to gamma. Okay. Now let's come to another theorem. Again, Hahn-Banach theorem, but this is for in here we will take, instead of real linear space, we can take complex vector spaces. The idea is same, just you have to replace R by C, and you know, if you have okay, if you have a complex valued function, say from X to C, so this is nothing but you can write it as f1x plus if f2x. So this f1 and f2 are real valued functions. Okay, so you have to use this idea. So what you do, you break f into two parts, real and imaginary part, f1 plus if2. So this you will get in your textbook. I will not prove this theorem. This is an exercise. Check your textbook for a proof. Here I mean by your textbook, I mean the book by Krejcik. So what does it say? X be any R or T vector space. P a real valued sublinear functional on X. So R is so P is sublinear function. I would not say functional because by functional, what do we mean by functional? Map f from X to the underlined field. So here underlined field are either R or C. Okay, so if underlined field is C, then this is not a functional, but it is only a function. Okay, it satisfies two things. Number one, this, and number two, if alpha is any scalar, it may be a complex number. Okay, so and it takes values in R. So Px is a real number, but instead of alpha, we will take mod alpha. So P of alpha x equal to mod. So this is sublinear functional. Then if f is a linear functional, say f from x to k, such that mod of fx less than or equal to px for all x in z, then there exists an extension of f from x to, oh sorry, so if z is a subspace of x and f is a linear functional on z, such that mod of fx is less than or equal to px, then there exists f tilde from x to k, such that f tilde is an extension of f and f tilde satisfies this. Sorry, it should be mod of f tilde if. Okay, so this is for your exercise. Okay, I'll stop here. Next time we will prove Hahn-Banach theorem for non-dismissive. Okay, so I'll stop here. Drop your attendance.
Okay, sir.